So today I'm going to talk about the role of adhesives in dimensional stability of laminated wood composite in general. And that's kind of a overview of a project that started as a collaboration between me and Dr. Hamid Valipour at UNSW, and then gradually expanded, and Zahra worked kind of on extension of this project as my first master's student at UVic. Okay, so here's an overview of what I'm going to talk about today. First, I'm going to talk about laminated wood composite. What do we call a laminated wood composite and why they are so important? Then I'm going to share with you some of the experimental studies we conducted on a few laminated wood composite like glue-laminated timber, GLT, laminated veneer lumber, and cross-laminated timber. They're all laminated composites, but there are some differences. So I'm going to talk about that. Then I'm going to explain the numerical model we developed, how we validate that using the above experiments. And we also use the numerical model to run some parametric study. And based on those parametric study, I'm going to talk about the role of adhesives in the formation of cross-laminated timber, an example of a complex laminated product, and I'll finish off with some conclusion. So what is a laminated wood? First of all, they are very popular these days because they are widely used in mass timber construction. It's made by combining different layers of wood, bonding them with the adhesive that we rarely see. There are very tiny lines, thickness of 0.1 millimeter. And these products are becoming very popular because of environmental concern and sustainability of these products. So for example, cross-laminated timber, which is shown here, consists of 0 and 90 degrees timber glued together. We can use them for sealing a roof of mass timber building. We also have glue-laminated timber, which all the timber along the grain are bonded. They're placed parallel together, bonded with an adhesive, usually a thermoset resin. And we can use them for columns, for example, as it has been shown. This building, Brock's Common, is 18-story, one of the tallest mass timber building. The only thing that is not timber is those elevator shafts that they are used for lateral stability. They are made of reinforced concrete. Such materials, laminated wood composite, they continuously interact with their surrounding climate as the relative humidity and temperature, indoor or outdoor, depending where they are used, varies. The product's mechanical behavior as well as their shape may change. So here you can see, like, this is a cross-laminated timber. If you use it as a wall, for example, it interact with the outside and inside. So this is exterior, this is interior. For example, in a rainy day, if the relative humidity of outside increases, then the moisture get into the wood because there's a moisture gradient, and that may lead to deterioration of properties or expansion and some warpage because we have 0-90 degrees wood, and wood is an orthotropic material. So it may lead to some deformations. Here's another example we have in Victoria Malahide Sky Tower. So that one is also a mass timber building, about 40 meters long. And the columns are made of glue-laminated timber. So as you can see here, inside we have this glue-laminated timber, but it's covered by some thin CLT layers, as well as some metal cladding. So the goal is to protect glue-laminated timber from moisture, but we still see the bottom of the glue lam is exposed to outside, and the relative humidity of outside may change. So we want to see what's that effect of moisture variation on the mechanical property as well as the structural performance could. So The experimental study first initiated at UNSW, University of New South Wales in Australia around 2017. 6 different groups of laminated wood composite were considered, 3 hardwood glue lam and 3 softwood. So these are the softwood beams and these are the hardwood beams. So the anatomy of softwood and hardwood are a bit different. So that's why we're curious to see how that anatomy change leads to behavior in moisture change. So we look at these materials when we expose them to increase of moisture, sorption curve, and desorption curve. So during this cycle, we took some tiny cross sections of these beams and we measured the dimensional changes in horizontal in this direction as well as vertical direction. We also measured the thickness of these to calculate the longitudinal changes as well. And because we did the test at 2 different temperatures, 15 and 50, we also managed to calculate the coefficient of thermal expansion, which I denoted by KT here. And these are the wood species we use. So we use these acronyms to highlight the products we consider. So when you look at wood, depending on which section of a tree it's cut from, under moisture changes, for example, if we dry them, they can shrink. And they shrink more in the tangential direction to the grain rather than the radial direction. So that's why this leads to some warpage. So depending where the wood is taken from, under moisture variation, you may have such warpage and twist in wood. Or if you glue different pieces together, they kind of average out. So it is known in industry that glue-laminated timber or LVL is more dimensionally stable. So we wanted to quantify that. So here on the left, you see change in the strain versus moisture changes for horizontal, vertical, and longitudinal direction. So in other words, we check the dimension, we measure the displacement or deformations in this, and out of the plane direction. And we started from very dry sample up to very saturated samples. And interestingly, we saw a bilinear pattern. For wood, it's mainly known, it's like linear and then flat. So after moisture content about 28 to 30% moisture content, then the deformation doesn't occur much. So we assume everything is dimensionally stable. So for different samples here, we have different curves. So this is for radiata pine. So we created 6 times 6, 36 figures for sorption, desorption curve. This was part of the PhD thesis of Ali Reza, who was a PhD student at UNSW at that time. So he created all these figures and we tried to understand them. So we plotted them in these figures. So here you see for each wood, like glue lam product of each wood species, we have a coefficient of moisture expansion and moisture contraction plotted, and they are different. So for example, sorption at 15 degrees, it means it's expanding. So that's coefficient of moisture expansion. In horizontal direction, it's a little bit higher than coefficient of moisture expansion in the vertical direction. And you see the first 2 bars are for 15 degrees. The second 2 bars are for 50 degrees, and the blue bars are shown for thermal expansion because there was a change of temperature. We could estimate the coefficient of thermal expansion for two different directions. They are plotted here. And for longitudinal direction, we denote them by KML, L for longitudinal, and KTL. So the blue bars here are for thermal expansion. You see in the longitudinal direction, if you look at the scales, they are kind of a bit less than these. So just pay attention to the scales here. But the trend we see is for hardwood samples, those coefficients in longitudinal direction are higher compared to softwood in longitudinal direction. For transverse directions, we don't see much of a change. The other thing we can say based on this figure is increasing temperature from 15 to 50 led to an overall reduction of 60% in the coefficient of moisture expansion, but only in the transverse direction. What does it mean? It means when we move from 15 to 15, there's a bit of reduction. And it's only applicable to transverse direction. For the longitudinal direction, we see that the increasing the temperature has an effect on coefficient of moisture expansion and coefficient of moisture contraction in the longitudinal direction. So those are some of the observations we made based on these experiments. Another interesting thing was if we divide the coefficient of moisture expansion in the horizontal direction by the vertical direction, we kind of get a ratio of 0.9 or around 1. So it means horizontal and vertical direction kind of expand at the same rate. And this is unlike just wood samples, because wood usually expands more in the tangential direction, and that's why we have these warpage. So it means by bonding them, we kind of make the product more stable in the transverse direction. And that's due to the moisture changes. In the longitudinal direction, however, we see that KT becomes comparable to KM. Or otherwise, we can say we can ignore the effect of temperature in the transverse direction, because if you go back to the previous slide, you see KT is kind of very small. The coefficient of thermal expansion is quite low compared to moisture expansion. However, for the longitudinal direction, that is not true. It's comparable. So the implication of that for design is that we cannot ignore the temperature changes in longitudinal direction, but in the transverse direction, moisture is contributing more to the formation than temperature. So that was kind of the lessons we learned from this experimental campaign. After that, we decided to look at CLT and see if CLT is also very stable. So the short answer was not as stable as glue-lam in the in-plane directions, but let's see how we made that conclusion. So essentially, this is what we did. We had a CLT panel. We took cross-section in two different directions. We took these samples, and under sorption and desorption, we look at how they expand and shrink. But also, we cut the wood from some of these samples to look at how the clear wood, the building block of these CLT, expand and shrink, and see if we can use those data to simulate the overall expansion and contraction of these when they are bonded. So we use Norway spruce wood for CLT, and we monitor their expansion and shrinkage depending on the environmental cycle. in two different planes as well as out of plane. So when we say in plane, it's in the plane of the panel. Out of plane is through the thickness. So here these vertical lines are for measuring the out of plane. These horizontal lines are for measuring in plane. And depending on which cross section we have, the longitudinal direction could be on top or in the middle if we use the panel in transverse direction. We also measure the stiffness and strength of panels at different moisture content, because when we were doing simulation, we needed to know how wood properties, the mechanical property changes with moisture. So swelling and shrinkage of two sets of CLT specimen, as well as the individual layers, which were 20 millimeter thick. So each layer was 20 millimeter. The overall thickness was 60 for CLT. And each set comprised of 36 samples conditioned in two different temperatures at 15 and 50, just like the previous experimental campaign. And half of the specimen were oven dried, so no moisture, and the other half were saturated, kind of submerged in water to perform sorption and desorption experiments. And we measured 4 lengths because we wanted to see if the expansion on top and middle was the same. Because wood is oriented differently and we expected some changes. So these figures here is for after we dry the samples. So you see there's a more shrinkage here compared to middle section. And one interesting observation we made was when we saturated these samples in water, so moisture content of like 100%, and we fully dried them, we couldn't actually get a solid material. They always cracked. So this was unlike wood. So wood always warps, but not always crack if we slowly dry them. In this case, no matter how slow we dry them, we always saw a crack. So we thought there is a residual stress development here, which is higher than wood. And the only way we can check that is through modeling. That's why I did some finite element simulation to see if we can predict those residual stresses that are developed during drying cycles. So here you can see the results of just one set of the wood that has been cut. So these are not for CLT, these are just for wood layers. So for wood layers, we look at the parallel samples and perpendicular. We look at their deformation in the longitudinal and perpendicular to the grain direction, as well as through the out of plane or the thickness, how much it expands. So you can see in the perpendicular to the grain direction of wood, this coefficient, which is the slope of this curve, 2.3 and 2.4, is much higher than the parallel direction. And that kind of makes sense because wood is very strong in the longitudinal direction. It has a high stiffness and it doesn't expand or shrink much. In the thickness direction is about the same as this direction because it's a combination of kind of radial and tangential cells and they expand and shrink more. So in these two slopes are kind of the same, but interesting thing is after fiber saturation, in which in most design codes we assume the slope is constant, for this direction the slope kind of goes down, it's negative, while here it's kind of positive. So that needs more studies because we don't have that much of a confidence after fiber saturation point. But it begs the question, like, is this experimental or are these very valid? You see the slopes are consistent to each other. Like this part is very, very accurate, but this part things diverge. So we believe there is kind of a nano or micro scale effect there, and we need to do some multi-scale modeling in the future to understand that. Then we look at CLT. So here we look at in-plane deformation of CLT at two different locations, at the outer layers, up and down, or the middle layer. So based on the arrangement of the wood, we expect that the coefficient of moisture expansion is higher in the outer layer because it transfers to the grain, and the slope is like around 1. If you remember in the previous slides for wood, it was about clear wood samples, it was about 2, so twice higher for wood and half for CLT. In the middle layer, when we are looking at expansion parallel to the grain, the coefficient is even 10 times lower. So it means CLT is more stable along the grain direction. And these two coefficients are like 10 times different. In other words, the surface or the faces of CLT expand and shrink more than the middle layer, although their shrinkage is still less than wood, but it's not homogeneous because the material is layered. So they don't really shrink the same through the thickness of the panel. So this was the first time that we reported such distinct behavior of the outer layer compared to the middle layer. So to better understand this effect, I did some finite element modeling. Here we look at like a quarter of this model because of the symmetry we have. So we look at just a quarter of the model and we meshed it. We use a very fine mesh through the adhesive layer because it was very thin. So we need a refined mesh, and gradually I use a coarser mesh because we were very interested in changes here. And there were a lot of, actually the gradient was quite high across the grain, across the adhesive layer. So in order to capture that, and our results are accurate, based on the convergence study, we got to this mesh pattern. So then for the coefficient of moisture expansion, for example, if you're simulating the expansion of these panels, we use those slopes we got from the experiments on solid wood, and then we use it as an input for CLT simulation. For adhesives, there were not any reported data. So we looked at some thermoset adhesives, and we found the coefficient of moisture expansion for adhesives, mainly thermoset, is about 0.003%. And we consider that in the simulation, we found the effect was not that significant. So, and we found very good match between the experiment at the initial step, and that kind of validated the model. So these are the moisture expansion of the top and bottom layer, and this one is for middle layer. You see, if you look at the scales, you see for the middle layer, similar to experiment, we got a lower slope, and here I've zoomed out to show there are distinct behavior for temperatures and sorption and desorption cycles. For the middle layer, for the top and bottom layer, they were a bit different, but we capture that with the FE quite accurately. And here on the right, you see the deformed shape of the samples when they were saturated from dry state. So when it was dry, everything was rectangular. When it's like moisture content of 30%, moisture content of 100% fully water, like for example, there's rain and all the CLT becomes wet. If it's exposed, you see a lot of deformation, the outer layer, which is the weaker layer here. And here you see the 3D image of the deformations. So the middle of the panels, they expand less, but the sides, the edges, they expand more. So imagine if you have two CLT coming together, they can essentially create some buckling, and the floor panel may buckle if there is no gap between them. So this suggest we should have considerable gap between two panels if they are laid in a, for example, bay of a building when you're designing that. So using the 3D finite element model we developed, we can also look at the stresses that are developed. So we found considerable stress that is developed from dry state to moisture content of 28%, which is the fiber saturation. So relative humidity of 100% highlights the moisture content of 28%. So it means in a very humid day, if you have this CLT placed outside, you're going to have significant stresses in the, if this is Z direction, in this direction, so that pulls on the wood and you can have some maybe cracks here. But interestingly, the rolling shear stress was also significant. So that explains if you want to have if there's a possibility of having a rolling shear failure just to moisture changes, it may either occur here or at the here. So essentially at the boundaries of the samples. If you want to have perpendicular to the grain failure, it may occur in the middle. So different patterns. So we can check the cracks and visually see if this is true or not. Other interesting observation we had was about von Mises stresses in adhesive layer. We find quite significant, like about 10 megapascal can be induced just at the resin layer. So that highlights that we may have adhesive failure at the boundaries of the laminated timber when we make it quite wet. And the other thing I should mention for laminated fiber reinforced composite that we use in automotive and aerospace applications, the lamination usually starts at the edges. So we have an edge effect that highlights edges are susceptible to stresses. And we see that here again, that possibility is the same for laminated wood composite because the mechanics is the same. Now, if we look at the model that has been validated with the experiment, we can run a bunch of parametric study to optimize a more durable product. So for example, if we want to minimize those deformation, we have a bunch of different wood species we can use. We can use for the same even species, high quality and low quality. So in order to represent that, we use 20% higher modulus properties for elastic constant. And we saw that for regular spruce that we have, they kind of match very well with the previous results. So this shows using low or high quality doesn't affect the dimensional stability so much. However, if we come up with a wood species that have a higher shear modulus in the 2-3 plane, we can reduce the expansion of the panel at the edges quite significantly, like by half. So in other words, if we can find a wood species that has a very high G compared to its E, like if we divide those two ratio, for most of the wood, they're kind of the same, except few species. And this means if we can use those wood species, for example, for the top layers and use low quality for the middle, we may come up with a better product that we can use for our buildings. So we took this research a bit further with Zahra, my previous master student. We look at the effect of moisture diffusion coefficient when we have a transient phenomena that's happening here. For example, if we expose the two edges of CLT to different moisture contents when we have a moisture gradient, what happens? This is another step of complexity, because before we made sure all around the CLT was the same relative humidity. So in other words, left and right didn't change much. Here, we expose one surface to higher relative humidity, and we try to model the moisture transport, and based on the moisture transport, we try to compare the results. So for the modeling, we simulate the adhesives as distinct layer of 0.1 millimeter, and the red shows the higher relative humidity, so the humid outside, for example, and inside, like a regular layer, relative humidity of 65%. We use some inputs from literature, diffusion coefficient, equilibrium moisture content for outside and inside, and the different densities for the spruce and PUR adhesive we use for CLT. So if you look at the case of solid wood, when there is no adhesives, after a few hours, we see there is a kind of a gradient that is created. So the exposed side to higher moisture, we have a very high moisture content. Inside, which is dry, we have low. As time goes by, we get to this steady state. Now, if we have adhesives, we saw some jumps across the layers, and these jumps makes the product susceptible to delamination, because we can have the top of the adhesive expands more than the bottom, that creates a gradient of deformation and stresses. So with some assumptions, we try to make sure we can capture this trend, and we manage to get that. Now, we'll look at some case studies, because we compared the result with experiment, and we found we can capture this trend quite significantly. So if everything is constant, all the properties are the same, by just decreasing the diffusivity of the adhesive, that tiny 0.1 millimeter, and we see the moisture profile changes quite significantly here. So by decreasing diffusivity, everything shifts here. For the surfaces, not much of a change, but the middle layer, we see a more drastic decrease. So if we assume the adhesive is the same, and we just look at making CLT out of different wood species, we saw, wow, quite different profiles can be created. And that means if the CLT is made of different materials, of different wood species, we may have quite distinct deformation behavior. So here you can see the diffusion coefficient for different wood are different quite significantly. And for bamboo, for instance, which is not a wood, but a natural material that we use in some part of the world as an alternative to wood, we see that it has the potential to have reduced jumps across the layer, because its combination of diffusion coefficient with adhesives are so close that leads to low gradient across this. So essentially, bamboo, laminated bamboo, can be more dimensionally stable than laminated timber, for example. So we saw even for bamboo, we can make it even more optimized if we look at adhesives that are available for this. So based on this parametric study, we found that PVAC, polyvinyl alcohol, or acetate, is making the product more uniform, like expands more uniform, and then we can look at also the stress development, and that's what we did here. So to validate the model, we look at the stress distributions, compare it with experimental study that was done like around 2 decades ago in Germany. So here you can see the experimental data on the moisture-induced stresses. And we saw that as time goes by, those stresses are increasing and reaching a plateau. And our model kind of captures that. So again, here we just model half of the samples, and we can look at stresses, 2 different layers. And interestingly, we see that depending on the wood species and the adhesive we use, these stresses could be reduced quite significantly in each layer. So in other words, we can use this FE model as a tool to minimize induced stresses. And moisture-induced stresses essentially can be reduced by selecting the combination of wood and adhesives smartly rather than trial and errors. We can use this as a tool to design more durable products. So for example, here, if we use pine and PRF for a current design, if we use oak and PVAC, the stresses could be reduced from 1.7 megapascal to about 0.45. So we can look at the ultimate stress and failure of wood species and try to always be below that at the extreme cases. For moisture-induced deformation, we tried to simulate an experiment that was done by Thomas Grecki in Switzerland. So we had these panels exposed to a moisture gradient of 100% over 65%, relative humidity. So this part was all water. Here was exposed air, and it was sealed all around. So with these dial gauges, they tried to look at expansion of the panels in the transverse direction, and they define a parameter called cup deformation, which shows how much curvature you get when you expose the panels to moisture. So we did that with ANSYS. We modeled this at 3-layer, so 0 for the top and bottom, and middle 90 degrees. So here you see the wood grain direction here. And here's the simulated result. It's not quite symmetric because if you look at the experimental setup, the supports we have is not quite symmetric. So that led to a little bit of a unsymmetric deformation here. And for the inputs, we use the we use modulus of elasticity in different direction that changes with moisture content. So we consider that, and we compare the overall shape and the maximum deformation we have here with the experimental data. So on this slide, you can see cup deformation based on the measurements and our FE model. There are some errors that can be attributed to assumptions like constant diffusion coefficient with moisture. So as the moisture content changes, the coefficient of moisture expansion may vary as well, but we assume constant. And then the cup deformation, the maximum deformation of the corner were also measured, but there was no reported data. So if we want to design more experiment, we can consider those to validate the model better. So based on the results, we look at 3 different adhesives that we can use for making the product. So for example, if you use PVAC, we expect to have a more durable product. And when we look at the cup deformation, we see that the spruce PVAC, which had a more uniform moisture profile led to a less cup deformation. And if you want to quantify that, it's about 10%. So by just changing that tiny adhesive layer, we can make the product more dimensionally stable. And that's due to the high diffusivity of PVAC. Essentially, the moisture can transport from layer to another layer much faster and easier. So we also look at some cases when the adhesive modulus has been changed, but the effect was found to be less than 5%. In other words, if you're going to design a new adhesive, you better focus on its diffusivity rather than modulus. And it kind of makes sense because the modulus is for just a 0.1 millimeter. So it shouldn't affect the product more, but that adhesive layer can act as a moisture barrier. So creates these moisture jumps that consequently leads to jumps in stresses, and we see the exhibition of that as a cup deformation. So with all these results that I presented, we can conclude a few key facts that we discovered. First, temperature has a considerable effect on coefficient of moisture expansion and coefficient of moisture contraction of CLT, but its effect on the wood layer is not significant. So that's based on the experiments we found, and we kind of, with modeling, we understood why. The effect of temperature on in-plane dimensional changes is more pronounced compared to the effect of moisture. And again, we say in-plane, and that was kind of the same for glue-laminated timber. The effect of effect of temperature out of plane was found to be not significant compared to the effect of moisture. So that again helps us with some provisions in the code in the future. Although gluing or adhesive bonding of wood layer in perpendicular directions leads to a more uniform expansion and contraction, significant stresses can be introduced because different layer expands at different rates. That creates some significant stresses. And we show that the magnitude of those stresses are quite significant, and they can lead to cracks, splitting, delamination, which we call it glue failure. In the future, when we have like a suddenly one humid day after a dry day, and with this climate crisis we have, that's possible, we can use finite element to optimize our product even more. Modeling shows the stresses were significant and there are possibility of rolling shear failure, and glue can also fail. So both wood and glue can fail. As the moisture diffusivity increases, the formation is reduced. So for the first time, we kind of discovered this phenomenon. So at the end, I would like to acknowledge my collaborator and my student. So first of all, Professor Valipur, who started this collaboration with me, with PhD student Ali Reza, who is now graduated and is a postdoc at University of Melbourne, and also Zahra. She helped me a lot with the transient analysis and moisture transport in layered wood composites. And if you want to know more about this study, the research campaign we conducted, they have been published in 3 papers in construction and building material. And with that, I would like to thank you for attending and listening to my talk today. If you have any question, please start your question.